We are looking at something absolutely mind-bending today in this explainer. We're talking about the invisible, microscopic forces that literally hold our entire universe together, atomic structure and interatomic bonding. But, to wrap our heads around these super abstract subatomic concepts, we're not going to start in some sterile lab. No, we're going to kick things off with a totally everyday macroscopic phenomenon. Let's head to the tropics and look at a true marvel of nature.
Take the gecko, right? It's just this harmless little tropical lizard, but it possesses a literal superpower that has had scientists scratching their heads for decades. It has this wild, almost physics-defying ability to sprint up vertical walls and just hang out upside down on pretty much any surface, even ones that look completely smooth to the naked eye. Okay, let's really dive into this. How on earth is this possible? How can a creature sometimes weighing several ounces just casually hang from a glass ceiling supported by literally one toe? There are no suction cups happening here, and it's definitely not oozing some kind of sticky biological glue. Actually, scratch that. It's way cooler. The answer lies entirely in the realm of atomic interactions. To figure this out, we've got to zoom way in. If you look microscopically at a gecko's toe pad, you'll see it's absolutely covered in millions of incredibly tiny hairs. And because there are so many of them, and they are so impossibly small, they can get intimately close to the molecules of whatever surface the gecko is walking on. When they get that close, they trigger what are called van der Waals forces. These are weak, attractive forces between the molecules in the hairs and the molecules of the wall. So, to let go, the gecko isn't breaking a glue bond. It just curls its toes and mechanically peels those little hairs away. It's brilliant. So why does this matter to us? Well, by figuring out this biological trick, human engineers have actually been able to mimic it. Scientists basically stole the atomic principles right off the gecko's foot to create ultra-strong synthetic adhesives, like groundbreaking surgical tape with a really complex microscopic structure. They use this stuff in operating rooms to close wounds instead of traditional sutures or staples. It holds tight, even if it gets wet, it's completely biodegradable, and it's non-toxic. And the whole shebang exists simply because we finally understood how atoms interact.
Section 1. Inside the atom. Zooming in. To really grasp how these incredible interactions happen, we have to go past the microscopic and jump straight down to the fundamental building blocks of matter, the atom itself. Right at the center is a tiny nucleus, packed with positively charged protons and electrically neutral neutrons. And swarming all around that nucleus are negatively charged, moving electrons. What's crazy to think about here is the scale. The masses of these particles are just unfathomably small. But the protons and neutrons are way heavier than those orbiting electrons. Now, a chemical element's actual identity, its atomic number, or Z, is defined purely by the number of protons in its nucleus. Add the neutrons to that, and you get the atomic mass, or A.
But, nature loves to throw a curveball. The number of protons is totally strict, like carbon is always going to have 6 protons. But the neutrons, they can actually vary. When you have atoms of the exact same element rocking different numbers of neutrons, we call them isotopes. So an element can exist out there in nature in a few different versions with slightly different atomic masses. Because of those isotopes, when you look at the periodic table, the atomic weight you see isn't just a clean, simple integer. It's actually a weighted average. If we look at the math for cerium, for instance, we don't just see one single weight. Cerium has 4 naturally occurring isotopes. Now, the vast majority of it, like over 88%, is cerium-140. But there are these tiny little fractions of cerium-136, 138, and 142 mixed in there too. So if you multiply each naturally occurring isotope by its fraction in nature, it grounds the math perfectly. It's really just a heavily weighted average.
So how are we supposed to picture these atoms? For a long time, we relied on the classical Bohr model, treating the atom like a tiny solar system where electrons orbit the nucleus on neat, perfect little circular tracks. Super easy to visualize, but yeah, it's pretty limited. Quantum mechanics came along and showed us that electrons definitely do not travel on perfect little train tracks. Enter the modern wave mechanical model. Here, the electron acts like both a particle and a wave. Its position isn't a fixed orbit, it's a probability cloud, basically a fuzzy map of where the electron is most likely hanging out at any given moment.
Section 2. Mapping the electrons. Even though these electrons are just buzzing around in these fuzzy probability clouds, we can still precisely map their locations and energies. Think of locating an electron in this wave mechanical model exactly like finding a friend's house using a mailing address. We use 4 parameters called quantum numbers. First up, the city. That's our principal quantum number, which gives us the main electron shell or energy level. Next, the street. The azimuthal quantum number, this dictates the actual shape of the subshell, like S, P, D, or F. Then we need the specific house number on that street. That's the magnetic quantum number, telling us how the orbital is oriented in 3D space. And finally, since up to 2 electrons can live in the exact same house, we need to know which roommate we're looking for. That's the spin quantum number, which is always either spin up or spin down.
The shape of these orbital houses all depends on that second quantum number, the street. The simplest one is the s orbital. It's just a perfect sphere, centered right over the nucleus. A really beautifully simple probability cloud.
But things get way more fascinating as we move down the more complex streets. The p orbitals, for instance, are definitely not spherical. They have these distinct two-lobed dumbbell shapes. And depending on their magnetic quantum number, these dumbbells orient themselves along entirely different axes in 3D space. So stretching along the x-axis, the y-axis, or the z-axis. It's just an incredible way for us to visualize a totally invisible subatomic world.
Now, there are strict rules for how these energy states, these houses, get filled. The biggest one is the Pauli exclusion principle. This is a fundamental rule that says each specific electron state, each house, can hold a maximum of only 2 electrons, no more. And if they are going to share that space, those electron roommates absolutely must have opposite spins, one up, one down. This rule is a massive deal because it keeps the entire atomic structure highly organized, preventing all the electrons from just crashing down into the lowest energy level all at once.
Section 3. The periodic table.
All right, so we've zoomed in on how electrons organize themselves. Now let's pull back a bit and see how these subatomic configurations organize, well, the entire observable universe. The elements aren't just tossed onto the periodic table at random. Yes, they're situated by increasing atomic number, but their arrangement into horizontal periods and vertical groups, that is entirely dictated by their electron structure. Elements stacked in the same vertical column share the exact same number of electrons in their outermost shell, and because of that, they exhibit incredibly similar physical and chemical properties. When we look across the table, we see some major behavioral differences. Most elements fall under the metal classification and are electropositive. Basically, they are highly capable of, and actually really prefer, giving up their few outermost electrons so they can become positively charged ions. In stark contrast, way over on the far right side, you've got your electronegative nonmetals. These guys are hoarders. They aggressively seek out and accept electrons to fill up their outer shells, becoming negatively charged ions. So the crucial takeaway here is this. It all comes down to valence electrons. These are the electrons sitting right at the absolute outer edge of the atomic shell. They're the ones doing all the interacting with the outside world. Whether an element is electropositive or electronegative, whether it's a gas, a liquid, or a solid, whether it conducts electricity or shatters like glass, literally all of it is dictated exactly by how these specific valence electrons choose to interact, share, or steal to form solid structures.
Section 4. The forces that bind us. Zooming all the way back out to the macro scale, let's connect these quantum rules to the tangible world we interact with every single day, bringing it right back to our gecko clinging to the glass. It all comes down to interatomic interactions. See, when 2 atoms are super far apart, they essentially ignore each other. The interaction is negligible. But as they get closer, attractive forces start to develop. This is the sweet spot, just like those microscopic hairs on the gecko's foot getting close enough to the wall to feel that attraction. But watch out, because if those atoms get excessively close, their electron clouds overlap and massive repulsive forces kick in. The exact equilibrium point, that perfect Goldilocks balance, where attractive forces pull them in, but repulsive forces keep them from collapsing into each other, that is exactly what creates an atomic bond.
And that leaves us with a truly mind-bending paradox to think about. If every single atom is fundamentally composed of mostly empty space, and the outermost layer of every atom is a negatively charged electron cloud that inherently repels other electron clouds, how does anything in our universe actually stick together at all? Why doesn't your hand just pass straight through the table? Well, that incredible balance of forces and the wildly specific types of bonds they create is exactly what we're going to uncover next on. Thanks so much for joining me on this explainer, and keep questioning the world around you.